All things being equal, this will be the last video on indices and logarithm. It's been a very nice ride. Creating this content for people in high school writing exams like IGCSE, I think, GCSE, SSC, that's in West Africa and other parts of the world. Like if you're writing high school related exams like that, this has been a nice ride right here. I hope to do more of this. If there's a particular topic you like me to teach for high school people, maybe you're in high school, you have a kid in high school, a brother also in high school that is battling with any of these topics, just let me know. I might just be able to make a playlist for that. So let's go on to this final playlist for the indices and logarithms playlist, except something else comes up though. So we're looking at exponential and logarithmic inequalities. Exponential and logarithmic inequalities. Um, so we've had a very nice ride looking at indices, looking at logarithm. How about talking about their inequalities? Because they have some specific rules, we need to pay attention to some things, right? First of all, we have a brief review of exponents and logarithms. We have the exponential from a raised to power x, right? Okay, let me expand this so it can be bigger. So we have the exponential from a raised to power x, generally speaking, where a is greater than 0 and a is not 1. I think I made a mistake in a previous video to say to combine these two, we just say a is greater than 1. No, that won't work because this a still holds for values between 0 and 1. Say a could still be 1 over 10, it could be anything, it could be 0.75, it could be all that. So that it won't be right to say a greater than 1. No, that won't be right because it also holds for values between 0 and 1. So a holds for values between 0 and 1 and values bigger than 1. But it must be greater than 0, but it must not be 1. So if a is greater than 1, we have, so for instance, if a is greater than 1, it is an increasing function, okay? But if a lies between 0 and 1, the function is decreasing. And that's why I said you can have values between 0 and 1. So that's why it won't be right to say the combined something is a greater than 1. That won't be correct. Then we go for logarithmic form now. So we have the logarithm from log a x to base a, right? So this is defined only when x is positive, because if x is not greater than 0, this won't work. Then of course a itself, so it's like the condition for exponents hold for logarithm. In addition to that, then the argument for the logarithm must be positive. All right. So this is defined only when x is greater than 0 and when a is greater than 1, which gives increasing function. And when a lies between 0 and 1, it gives a decreasing function. So that's like a quick review of that. Now let's talk about some key rule for exponential inequalities. Okay. So for exponential inequalities, case one, if the base is greater than 1, for instance, if a is greater than 1, then a raised power x greater than a raised power y implies that x is greater than y. I think we've encountered this kind of thing in a previous video. I think talking about exponential equations or so, or comparing exponents. Okay, so the inequality sign stays the same. If a is greater than 1 and you have a raised power x greater than a raised power y, that means x is greater than y. Then case 2, if we have the base between 0 and 1, that is 0, a lies between 0 and 1, meaning that the base is like 1 over 10, 0 0.5, 0 0.323, whatever. So in this case now, because it's between 0 and 1, a raised power x greater than a raised power y implies that x is less than y. And that makes sense, right? Generally speaking, if we have, that makes serious sense because if we have, let's say we have 3 raised to power x greater than 2 raised to power y. Of course, 3 and 2 are both greater than 1, right? Or they are both yeah, they're both greater than 1. So as a result of that, this simply implies that x, oh, okay, no. This is what I should be doing here. So if the base is the same, 3 raised power x greater than 3 raised power y. We know 3 is clearly greater than 1. So it's clear that 3x will also be greater than y here, no matter so for the condition for them to be greater is this. But on the other hand, what if you now have 1 over 3 raised power x greater than 1 over 3 raised power y? Okay, now see what happens here. You have that 1 over 3 lies between 0 and 1 now. Okay, that's the condition here. So what does that mean? Okay, let's even do some practicals, some practice. Like if you have 1 over 3 raised to power 1, that's 1 over 3. How about 1 over 3 raised to power 2? That's 1 over 9. So, and clearly, yeah, if you divide 1 into 3 places, you get bigger chunks than when you divide 1 into 9 places. Okay, so it means that as the power is increasing here, the number is getting smaller. So that's why when you have a number like 1 over 3 that is between 0 and 1, this implies that x is less than y. Okay, so for this to be greater than this power must be smaller than this power. That's what that the rules are telling us right there, and they make sense, right? So uh so if you have a base zero a between 0 and 1, it means a raised by x is greater than a raised by y, which implies x is less than y. The inequality sign then reverses in that case. So you want to pay attention to the base before you make that decision. So we have 20.3 where we talk about method for solving exponential inequalities. So the first thing is to solve exponential inequalities, you rewrite both sides with the same base, compare exponents based on these rules we've done now, then reverse the inequality if the base is less than 1, just like we've said, and solve the resulting linear inequality. That goes like we have example 1 now. So example 1, we want to solve 2 raised power x plus 1 greater than 8. So we rewrite 8 as power of 3. That means 2 raised power x 8 is 2 raised power 3, right? That means 2 raised power x plus 1 is greater than 2 raised power 3. And because since the base is greater than 1, 2 is greater than 1, then we can keep this and we just say x plus 1 is greater than 3. If you subtract 1 from both sides, we say x is greater than 2. And that really makes sense because here, if x is greater than 2, it means we start from like 2.1, or let's take the next integer, that's 3. So 2 raised power 3 plus 1. Uh, okay, x is greater than 2. So if x is greater than 2, that's like 3. Okay. And that is 2 raised power 4. It's not greater than 8, though. Is everything fine there? Um, x plus 1 greater than 3. So, yeah, so we have x is greater than 2. X is greater than 2. 2 plus 1 is 3. Okay, x is greater than 2, sorry. So it has to start from 3. 3 plus 1 is 4. 2 raised by 4 is 16. Okay, yeah, I get it. I think I was thinking in another way. Okay, that works. Okay, so look at example 2 now. You have 3 raised by 2x less than or equal to 27. Okay, so 27 is 3 raised by 3. So we have 3 raised by 2x less than or equal to 3 raised by 3. Then you can keep the direction. So 2 raised by x is less than or equal to 3 because 3 is greater than 1. So we don't have to reverse the sign when we compare exponents. So 2x is less than or equal to 3. That means x is less than or equal to 3 over 2. Now, look at the case of base less than 1. So solve 1 over x, 1 over half raised by x greater than half raised by 3. Now, because half is between 0 and 1, you reverse the inequality. That means x has got to be less than 3. Because if x is less than 3, let's say x is 2. So 1 over 2 raised by 2 is 1 over 4, whereas 1 over 2 raised by 3 is 1 over 8. So, and this is clearly bigger. 1 over 4 is clearly bigger than 1 over 8. So that's a simple analogy there to be well understood. So, example 4 now. So what if you talk about different bases? You have 2x, 2 raised by x greater than 7. The bases are not common. You can't write them in the same base. So you can take log of both sides. If you had e somewhere, you take natural log, but without e, you can take common log like we have now. So we have log 2 raised by x is greater than log 7. So log 2 raised by x is the same thing as x log 2. Because from the log rule, the power comes down to multiply the log. So we have x log 2 greater than log 7. That means x is log 7 over log 2 if you divide both sides by log 2. And of course, you can then punch your calculator for log 7 all over log 2. So log 7, okay, all over log 2, all over log 2. And we have 2.807 roughly 2.81 approximately. So x is greater than 2.81 like that. Okay, so that's how that goes. Then we have some key rules for logarithmic inequalities. So we've had the rules for logarithmic exponential inequalities. For logarithmic inequalities, we also consider the two bases. For base greater than 1, if a is greater than 1, we have log x to base a should be greater than log y to base a. We keep the sign x is greater than y, right? Sign stays the same. Same thing if the base is between 0 and 1, like a is between 0 and 1. So log x to base a greater than log y to base a will imply that x is less than y. So it's just the same for like the one for exponential form. In that case, the sign will reverse. So what happens? We then in this case, in addition, we now have to check the domain rules. So for any logarithm now, all the arguments should be greater than zero. Okay. So like x should be greater than zero, y should be greater than zero. So you have to be sure of that. So we take example 5. Now, example 5 says log x to base 2 is greater than 3, right? So if you convert to exponential, you just know that x is greater than 2 raised by 3. That means x is greater than 8, and that works. Okay? So we have example 6. For example 6 now, see what happens. We have log x minus 1 to base 3 less than or equal to 2. So um, to check the domain, x minus 1 should be greater than 0, meaning that x is greater than 1. So we keep that and be sure anything at the end of the day, anything we get should be greater than 1. So convert to exponential form now. So in exponential form, you have x minus 1 is less than or equal to 3 raised by 2. That means x minus 1 is less than or equal to 9. That means x is less than or equal to 9 plus 1, which is 10. So in this case now, we already have this domain here that x must be greater than 1. So in this case, so we then have that 1 is less than x because that is compulsory. You cannot go below this. So you have 1 is less than x less than or equal to 10 that you already have right here. Okay. So for in example 7, see what happens here. Okay, I think this is a long story. Uh Okay, I have to look at it in bits and pieces. In example 7, see what we have. We have log x plus log x minus 3 greater than 1. So that means, first of all, x has to be greater than 0, and x minus 3 has to be greater than 0, meaning that x is greater than 3. So overall, it means x should be greater than 3, which is stronger than x greater than 0. So what do we then have? You can use the law of logarithm. So you have log x plus log x minus 3 means log x times x minus 3, and that is greater than 1. So what do? We convert, we do the exponent conversion. So we have x into x minus 3 greater than 10, because log here, if you see log and you don't see the base, that means 10 raised power 1. That means the base is 10. So we have x into x minus 3 greater than 10 raised power 1. So that means if you expand, you have x squared minus 3x greater than 10. If you bring the 10, you have x squared minus 3x minus 10 greater than 10. So in this case, it looks like we can factorize. We can have minus 5x plus 2x. So we have minus 3x. So we have x minus 5 into x plus 2 greater than 0. Now, solution of the quadratic then means we have x minus 5 greater than 0. That means x is greater than 5. Then x minus 5, x plus 2 greater than 0. That means x is less than 2. No, that means x plus 2 greater than 0 means x is also greater than 2. That means I think there's something here. Okay, for us to get something greater than 0, both of them must be, we want to get something greater than 0. So if it's either, okay, if x, it's either, this is this is negative, and this is, I think they both have to be negative, right? For both of them to be greater than 0, they both have to be negative. So x minus 5 less than 0, we have x less than 5. Okay. 5 minus 5, 0. And then we have, okay. So for solutions of the quadratic, we know we are going to get minus 2 here and we get 5 here. So we have x is less than minus 2 on the negative side, and x is greater than 5 on this other side. So but the domain is x greater than 3, so we go for x greater than 5, like that. That can be a bit confusing. Okay, so for example 8 now, we solve e raised power 2x less than 5. So take the natural logarithm. We are taking natural logarithm because we have e here, and we need to easily cancel out. So we have ln e raised by 2x equals ln 5. So that means we have, ln e will go, so 2x will be left. So 2x equals ln 5. So x is ln 5 over 2. We can easily use calculator for that. And, that one has no serious confusion. The next, solve ln x plus 4 greater than or equal to 0. Of course, just stick to exponential form. So you have x plus 4 greater than or equal to e raised power 0. That means x plus 4 is greater than or equal to 1. So subtract 4 from both sides. So you have x greater than or equal to minus 3. So for the domain now, x plus 4 should be positive. That means x should be greater than minus 4. So, but here, for x greater than minus 4, interestingly, x is greater than or equal to minus 3 here. So that means it's a valid answer because minus 3 is greater than minus 4. All right. So since x is greater than minus 4, then since minus 3 is greater than minus 4, then the final answer is that x is greater than or equal to minus 3. So in summary, we have that if a is greater than 1, we keep the inequality sign. And if a lies between 0 and 1, we reverse the inequality sign. For logarithms, argument must be positive in addition. If bases cannot be matched, we can take logarithms. So that's what we've seen so far. And it is a kind of summary of even all the methods you have applied in solving logarithms and indices previously. Okay, so solve the following inequalities. Give your answers in interval notation where appropriate. Okay, what should I do here now? Hmm, what do we do? Okay, I think I see this particular problem here. I think I like question 4. Maybe I should go for that. Yeah. Question 4, 1 over 3 raised by x minus 2 less than 9. 1 over 3, 1 over 3, 1 over 3 raised by x minus 2, 1 over 3 raised by x minus 2 less than 9. Okay, less than 9. So what can we do here? Well, they are not, it's not 1 over 3 on both sides. So we can try to do this. We know this will now be 3. 1 over 3 is the same thing as 3 raised by minus 1 raised by x minus 2 less than 9. So we know that will be 3 in 3 raised by minus 1 into x minus 2 less than 9. Okay, so that means 3 raised by minus x plus 2 less than 9, right? And that is like 3 raised by 2 minus x less than 9. Okay, so we can then comment that since okay, this less than 9. This 9 can also be written as 3 raised power 2. Okay? 9 is 3 raised power 2. So we can then say, since 3 is greater than 1, then we'll maintain this direction. So then 2 minus x should be less than 2, like this. So that means that 2 minus 2 is less than x. That means we transfer this here and transfer this here. So 2 minus 2 is less than x. That means 0 is less than x, meaning that x should be greater than 0. Okay? It wasn't a Okay, it was an exponential problem, so we don't have to worry about the domain. So x is greater than 0. Does it work? So if x is greater than 0, for instance, so if x is 1, okay, we have x, for x being 1, that means we have 1 over 3 raised by minus 1. So, and that is 3 raised by minus 1 times minus 1, that's 3 raised by minus 1, which is less than 9. So that works actually. So x is greater than 0 in that regard. So the next thing we want to do is to check another one. Which of this will do the job again? Okay, I'll go for 20. It looks the most complex. I'm not sure. It may not be as complex as I think, though. But we have log x squared minus 5 to base 4 greater than 1. Log x squared log log x squared minus 5 to base 4 is greater than 1. Final check to be sure. Log x squared minus 5 to base 4 is greater than 1. Okay? Greater than 1. So we go. Now, we can write in exponent form. So we have x squared minus 5 is greater than 4 raised power 1. Okay, so then we have x raised power 5. X squared minus 5 is greater than 4. So that means we have x squared is greater than 4 plus 5. So that means x squared is greater than 9. So in this case, it means that x is greater than plus or minus square root of 9. Okay, so that means x is greater than plus or minus 3. But then, is it a log problem? Yeah, it was a log problem. So we need to get the domain. So domain restriction. So domain restriction, we have to check that. So for the domain restriction, we know that x squared minus 5 should be greater than 0. That means that x should be greater, x should be x squared should be greater than 5. That means x should be greater than plus or minus root 5. Of course, x should be greater than plus or minus root 5. So that means x should be, this is a bit tricky. X should be greater than or plus or minus root 5, right? So that means we can have the two conditions now. X is greater than minus root 5, and then x is also greater than plus than root 5. We have those two. So in this case now, so I think we have to take the stronger one, because if x is greater than minus root 5, if x is greater than root 5, it's automatically greater than minus root 5, so we can cancel this. So the strong thing is that x should be greater than root 5. So yeah, because x has to be greater than root 5 now. This doesn't even stand a chance, okay? Already here, we have, here it means we have x greater than minus root minus 3, right? Okay. No, I mean, this can be confusing, but it's okay. So this is x greater than minus 3 or x greater than 3 itself. Then root 5 is not up to 3, right? Okay, maybe we should even get the actual value here so that we can compare properly. So root 5 should be, let me just use a calculator. Square root of 5. Okay, we have square roots of 5. That is 2.2361. 2.23, or let me just take two decimal places, 2.24. Okay, so this is 2.24. So this is, it is greater than 2.24. Okay, greater than 2.24. So interestingly, we have x greater than minus 3, but our strong condition here is that x should be greater than 2.24. So x is not greater than, minus 3, the first one here, minus 3 is not greater than 2.24, reject. Okay, we reject minus 3. On the other hand, 3 is greater than 2.24, accept. So we can conclude. So x equals 3 is valid. All right. So with that, we come to the end of this interesting video on exponential and logarithmic inequalities, which can be a bit tricky. So you want to be really sure, because it can get very dicey at some points. And with this also, we come to the very end of the playlist on indices and logarithm. It's been a jolly ride. I think, yeah, it's been such a nice experience indeed. Don't forget to try your hands on the questions given so you can be sure you really understand all we've done. This is 1 to 10, and then we have 11 to 20. Let me know how helpful this whole thing has been for you. And let me know if there's something that I should try out to make it easy, better for you. Ultimately, if you have subscribed already, I thank you very much for doing that. If you haven't subscribed, the question is, why haven't you subscribed? Why not go ahead right now, subscribe, and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can become a member of this channel by clicking on join. That gives you special privileges like getting to see some videos first. And of course, you can also get to be the only one seeing certain videos as members. Then you can request my PDF notes. We can hang out together online or physically if you're in the same geographical zone to discuss whatever interests you on this channel, be it mathematics, data analysis, data science, machine learning, scholarships, writing books, all kinds of things, whatever it is that interest you here. Okay. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.